My name is Pierre-Clément. I am a PhD candidate at Penn State University, and I had the opportunity to do an internship at Idaho National Laboratory this summer. This video presents the research that has been done during this time at INL and shows how it could affect the world energy future. Solving the energy crisis is one of the greatest challenges that humanity is facing today. The energy consumption is rising around the world, and models predict that it will keep increasing in the future. The energy industry needs to tackle this issue while mitigating climate change for future generations. What we need is nuclear energy, a safe, sustainable, reliable, and economically viable source of energy. INL has played a major role in the nuclear industry's achievements by building unique experimental facilities like ATR or TREAT and developing advanced simulation codes like Moose, or Marmot, or Bison. Part of this research in modeling focuses on material behavior, and this is where this project comes to life. Let's give some of its context. If we take a closer look at the nuclear power plant, the energy is generated in the reactor core. It contains the fuel rod made out of fuel pellets and the cladding. Understanding the behavior of the cladding is crucial, since it prevents the release of radioactive material. One problem is that the cladding, made out of zirconium, is in contact with water. Corrosion naturally occurs at the interface, creating zirconium oxide as well as hydrogen. Part of the hydrogen created is picked up by the cladding and then creates hydride precipitates. These precipitates can be observed in the cladding as shown in this picture. Every black line is a precipitate in the cladding. These precipitates can be an issue because they facilitate cracks propagation, which could lead to the failure of the cladding. This project uses the multi-physics framework MOOSE developed by INL to model the precipitation of the hydrides. To simplify this presentation of the grand potential model, we will assume that we consider a two-phase system, composed of a precipitate phase and the matrix. This model can easily be generalized to an arbitrary number of phases. In order to describe this two-phase system, we need to introduce two variables. The first one is the chemical potential, which is the change in Gibbs free energy with respect to the composition. The second one is the order parameter eta. The order parameter is simply a variable that allows us to keep track of which phase we are in. Here is a picture of a precipitate in red in a surrounding matrix. The order parameter varies from 0 to 1, where 0 represents the matrix and 1 represents the precipitate, as shown on this graph here. Using continuous variable allows us to study the evolution of the system by simply solving partial differential equations. The first equation governs the evolution of the chemical potential. The first term here is analog to a diffusion term, and the second term corresponds to a difference in composition at the interface. The second equation governs the evolution of the order parameter. L is similar to mobility, and omega is what we call the grand potential. Deriving an expression for the grand potential was the main focus on this project. The grand potential takes into account the bulk free energy, the interfacial free energy, and the chemical free energy of the different phases. These contributions were already challenging to define and parameterize, but the greatest innovation was the introduction of the term corresponding to the contribution of the elastic energy to the free energy. Once a new formula is implemented in the code, a crucial step is to verify the new model by comparing the simulation results to the analytical solution. Here is a precipitate in a surrounding matrix, and the graph shows the profile of several components of the stress generated by the presence of the precipitate. The results of the model match the analytical solution pretty well. The only differences are located at the interface and are simply due to the continuous character of the interface in our model and the fact that the analytical solution is derived from a problem with sharp interfaces. These encouraging results mean that the grand potential model can help us study the chemical and material behavior of hydride precipitates in zirconium alloys. One big advantage that wasn't put forward in this presentation was the fact that this model is computationally inexpensive compared with previous models, which means that it could greatly accelerate the research in the area it could be used. The grand potential multiphase model is a great contribution to the multiphysics framework called MOOSE and would help the research on microstructure evolution.